Hi, this is Megan Dowd, and this is my week 10 assignment one, the planet analysis. So for this one, I created, start at the top here, the planet class, which each planet has its radius in year length. And then the main method here is the position method, where it finds the position on a certain day of that planet. So for a given day, I convert it into an angle using the 2 pi times day divided by year length over year length. And then we use cosine and sine to calculate the x and y coordinates from there in this main one. After that, I define the distance function. This takes 2 planets and a day. It gets their positions and then it computes the Euclidean distance between them using the basic formula. Next is the simulate distances function. This loops through a number of days and then calculates the distance from Earth to the other planets. I also included an optional noise parameter where I add normally distributed noise with mean zero and standard deviation. Then I have a plotting function which graphs the time series of distances and adds horizontal lines for the averages so they can be easily compared. And then we have our average distance matrix function, which loops through all pairs of planets and calculates the average distance between them over a long simulation period. So I also included a helper function to print this in table format. And then finally, we're to our main function. So I first defined the 8 planets with their radius and their year length. Then I compute the distance between Earth and Mars on day 732. So I ran that. Here it is 6.5, 246, and so on. Next, I run the 1,000-day simulation for Mercury, Venus and Mars relative to Earth, and these are the plotted results. You can see the periodic patterns in the plots because the planets orbit at different speeds. So, for example, our Mars here is our green one. Venus is the orange, and then Mercury is our blue as it has a faster orbit. So exiting out of that one, we get to continue on. So then I repeat the simulation with noise. I test the different values, and even as the noise increases, the average distances stay fairly consistent. Oh, it's going to be extra large. I pull in our other chart here. So again, very similar looking with Mercury being faster and so on. Finally, I run the 1,000-year simulation to build the 8x8 matrix of average distances between all the planet pairs. So this one might take a moment to run. Okay, so a few minutes later, I paused it and came back. We're finally done running our average distance matrix. So as you see here, this is the 1,000-year average distance. Mercury is still the closest to Earth, even 1,000 years. So yeah, that is my whole demonstration. Thank you.